Hello again, it is Dr. B, and today we'll be talking about molecules and compounds. Have a periodic table handy, you'll be using it frequently. We'll start by showing how to come up with reasonable ionic compound formulas, how to convert them into a name, or given a name, convert it into a chemical formula. And we'll talk about how they ratio out in terms of both mass and atomic ratios. So we learned in the previous lesson that ions form from metals when they lose electrons. These are cations. Other substances, group 7 substances, gain electrons to form anions. So if you found sodium on your periodic table, atomic number 11, look up at the top of that column. You should see a +1. That shows you that it has one valence electron. It will lose that negatively charged electron, leaving sodium from an atom now to an ion that is formed with a +1 charge. And I hope you can see that these will be attracted to each other. Positive to negative means an attractive force. So this will form sodium chloride, Na1Cl1. This is called an ionic bond, a metal to a nonmetal. There's one of each. Scientists drop the ones, and it is implied if you don't see those numbers. Why don't you try this one? Make sure it makes sense to you. If potassium combined with oxygen, well, potassium tends to only lose one electron, whereas oxygen gains two. So a molecular formula of KO does not make sense. You'll still have a -1 charge. However, if we have two of these, the 2 plus 1s will nicely offset the -2, and you'll get K2O. The faster way is to drop and switch. Take that 2, put it there, take that 1, put it there. You get K2O1, drop the 1, and that is the formula. The chemical formula for potassium oxide is K2O. What happens when calcium and chloride ions combine? Drop and switch, you'll see it's Cl2. Try combining aluminum ions and oxygen ions. You should get Al2O3. Now, I don't want to say too much about the substances that are exclusively to the right of the staircase. These are covalent substances, but I do want to point out a very simple bonding rule that tends to help so much. 95% of the atoms in your body belong to these 4 elements here. And if you just recall that hydrogen tends to form 1 bond, oxygen 2, nitrogen 3, and carbon 4, the mnemonic is HONC if you love chemistry, HONC, 1, 2, 3, 4. You can draw all sorts of substances that are not ionic compounds. They're more commonly referred to as molecules, individual substances that don't form a lattice. It's more common to use the term compound for ionic compounds that form a continuous lattice where it's a little hard to see where the individual substances are. Water, we have to draw it like that if oxygen is going to have 2 bonds. That means 2 lines. Do you see those 2 lines? And hydrogen, each one forms 1 bond. That's 1 line there and 1 line there. Similarly, there's only one way of drawing carbon dioxide, and it might not be apparent at first. How are we going to get 4 bonds on carbon if we only have 2 oxygens? Solution is to use double bonds. Try to write hydrogen peroxide H2O2, and you'll see the only way where you can have hydrogens with 1 bond and oxygen with 2 is to put both of the oxygens in the middle. Hint, put the thing that forms the largest number of bonds in the center and the thing that forms single bonds or the lowest number of bonds around the perimeter, and that'll be a good way to start. So those are all chemical formulas and how to draw them. The naming system's a little weird, but a lot of it students know already. I'll bet you already know that NaCl has the proper name of sodium chloride. I'll bet you know that CO is carbon monoxide. Therefore, there's a special rule. If it's an ionic compound, like a salt, like a metal to a nonmetal, don't use those monoditris. They get skipped for some reason. If it does both have elements to the right of the staircase, we do use the monoditri. These are not salts, these are called covalent substances. Both elements are to the right of the staircase. That's the dividing line between metals and nonmetals. Try AlCl3. Should we call it aluminum chloride or aluminum trichloride? Well, it is an ionic compound, so we'll go with aluminum chloride. This one is not, so we'll use the di, sulfur dioxide. And here's a new rule. If you're in the D block, use Roman numerals to specify the charge. Iron is in the D block, dead center. That's that big block in the middle, 10 columns across. And the oxides you can see from here and from here tend to form a -2 charge, but we do have two of them, and we accumulated a -4 charge, so we're going to call this iron 4 oxide with the Roman numerals. Silicon and oxygen are right of the staircase. We do use monoditri, so silicon dioxide will work just fine. Let's finish up by talking quickly about atomic and mass ratios. Well, atomic ratios are pretty simple. I mean, look at any of these things. 1 to 1, 2 to 1, 1 to 3, 2 to 3, and even some, all you have to do is reduce them down. For example, hydrogen peroxide is 2 to 2, but it's simpler to say 1 to 1. Mass ratios are more important because we can use a balance to actually make things, right? With no way do we want to count individual substances when they weigh so little. So recognizing that atoms have drastically different masses between them, we can look up the average atomic masses. These are typically the numbers with decimal places on your periodic table, and we can come up with them. The atomic ratio of nitrogen to hydrogen is 1 to 3, but a nitrogen atom weighs 14 atomic mass units. That's the units we'll use for now, just a relative number. And hydrogen atoms have a mass of 1 atom atomic mass unit, or 1 AMU. Therefore, since there's 3 of them, the ratio is going to be 14 over 3. Punch that in, and you'll see that's 4.67 to 1. Ammonia has 4.67 grams for each grams of nitrogen for each gram of hydrogen. That's a little bit about molecules and compounds.